Okay, it looks like they're closing the doors, so let's go ahead and get started. My name is Jim Sproch. I am a software engineer at Facebook, and I've worked on the React team for about 2 years now, almost 2 years. And today I'm going to tell you guys about how React.js renders your application. So let's get started. First off, React is a JavaScript library for building user interfaces. So what that basically means is that it sits in between the render output, in this case the DOM, or the browser, and the rest of your application. So React does not manage your application's like database. It doesn't manage your controllers. All it does is sort of take the state of your application and render it into a view. So in this sense, React has been called the V in MVC. That's one way of thinking about it. It turns out it can be a bit more than that once you start building an application in it. But as a first pass, this is a pretty good way of thinking about it. Today's talk is going to be, we're going to briefly go over the design of React, some prerequisites so that you know what's going on, you're not completely lost if you don't know about React. We'll talk about the virtual DOM, which is a implementation detail of React that allows React to achieve the high performance characteristics that it does. And that's sort of a foundational layer for the real interesting meat of the talk, which is reconciliation. That's the magic of how React actually does what it does. So we'll go ahead and dive right in. A React application is divided up into components. So this is very similar to a lot of other architectures. Basically, you could have a component that's as small as a text box that does some sort of input validation, all the way up to like a date selector, date picker, all the way up to like an image gallery or a full application. You can model your application as a single big component, and all the pieces of your application are subcomponents. You have components built on top of each other. So it uses composition pretty heavily. A React component is, in a sense, an idempotent function. What this means is that it takes the state of your application as an input, and it outputs some sort of user interface, some sort of UI, markup, HTML. So you could think of a React component as a function. It takes in some properties, and it returns some HTML. In fact, this is actually a perfectly valid React component. You can take this exact code, plop it into your application, and it will work. This angle bracket HTML mixed inside of your function is a syntax we call JSX. It's a syntactic extension to JavaScript. It's completely optional. If you don't want to use JSX, you could write it out with calls to JavaScript. In fact, this is what the JSX compiles down to. So there's a pre-transform that runs on the code and basically turns the HTML into something that looks like this. But this would be a typical React component. And to understand why React had to be built, we're going to go through a quick example of designing a component to see what it is that React is adding as value. Because there are lots of templating frameworks out there. So far, this just looks like templating. That's not really interesting or novel or useful. What is interesting is the way that React scales as your application grows in complexity. So let's take a look at an example component. We might want to have a notifications widget. We'll denote this as a bell. And the notifications widget has a few constraints, a few requirements. One of which is that if there's more than one or more than 0 notifications, we're going to display a little badge on top of the bell that says how many notifications there are. So if there's 8 notifications, we have a bell with a badge on it that says 8. Obviously, that number could get really big, so the designers had this idea that if there's more than 99 of these things, like it's 100 or more, then it's going to say 99 plus, and it's going to have a fire in the background. So you can see that the world is burning down, things are on fire. Pretty simple widget. 3 states, basically. So we can look at these 3 states and sort of show them on a diagram. And if you imagine that you had to have incoming notifications from the server, you'll have to transition from one state to another. So maybe we start off in the state where there's no badge and no notifications. It's just the empty bell. And we want to go to the state where there's 8 notifications, because we receive a message that like the user just got 8 Facebook friend requests. What we're going to have to do is we're going to have to add a badge, and we're going to have to set the badge's value to 8. So these are imperative operations. Basically, what we're doing is we're writing code to model the state transition from one initial state to the next state. And if we wanted to go from the empty bell to 99 plus, we would have to add a badge, add fire, and set the badge to 99 plus. So each of these operations is, or each of these state transitions is a set of operations, and you could go from any state to any other state, modulo the rules of your component. So if we look at what this code looks like, we're going to say if the count is greater than 99, and if it does not have fire, then we're going to add fire. Else, if it has fire, we're going to remove the fire, because count has to be less than 99 in this branch. If the count is equal to 0 and it has a badge, we're going to remove the badge, and then we're going to return. And if it has a badge, or if it does not have a badge, then we need to add a badge, because we're not in the 0 case anymore because we returned. And then we take the text, we figure out what the badge is supposed to say, we get the badge, we set the text to the string in there. I don't know about you, but reading this code is really hard to understand what's going on. Like, modeling state transitions this way is very difficult to reason about. And so it actually gets much worse if we add just one more state. So suppose that the designers come to us, they say, well, we thought we were done with this component. We thought that we built it to specification, everything was great, but we have this idea. We want to have this indeterminate state where we have a bell, and the bell has a red question mark in it. Why does it have a red question mark? I don't know, but that's what the designers came up with. So now we have one more state that we need to transition to. The issue is that if you look at the possible state transitions, there's a whole bunch more. Adding a single new state added a whole bunch of new transitions that could have occurred. And it turns out that this complexity, controlling complexity is like the essence of computer science. This is what we're trying to do, and the old paradigm does not control complexity well. It's madness. So we have state transitions. The state transition complexity is big O of n times n minus 1. Because you have n states, you can transition to any n minus 1 states. So the state transition complexity is n squared minus n. Which means that for every additional state that the designers decide they want to add to our application, we have a quadratic increase in the complexity of our application. And this is sort of what React aims to solve. This is this problem that we're solving. The root of the problem is that mutation is hard. What we're doing is we're taking a state and we're trying to mutate it into a new state. And that's something that's difficult to do, because we have to reason about all the possible scenarios and all the possible interactions, things that could happen. So let's not do mutation. Let's just completely avoid any sort of transitions between states. So how could we do this? One way we could do this is to basically go back to 1990, when everybody rendered web applications on the server. And when you want to render a web application, what you basically do is you go through a full set of sequences, you render from top to bottom. So you want to know how many items there are, you query the database for notifications, and you say, this is the number of notifications. And then you go through a very easy to follow logic. You set the text to whatever the correct value is. If the count is greater than 99, we have an image with the fire background. If the count is greater than 0, we set a badge, and the badge has the value of the text. Looking at this code, I know exactly what it does. You guys may not even know React, but you can just sort of look at this and intuitively know what it does. And that's the goal of specifying states and avoiding mutation. So effectively what we're doing is we're rebuilding the whole DOM for every change. So anytime we get a new piece of data, anytime that something happens, we're going to completely throw out the old DOM regenerate it from scratch, top to bottom, in a way that we can reason about. So we have one flow of control. We don't have all these branches and if statements. We have a single sequence of instructions that we understand. It's the same every time, and all you're doing is plugging in different data. So it's much easier to reason about. That sounds expensive. And in fact, if that's actually what we did, it would be expensive. It would be prohibitively expensive. But we have a solution to this. What we use is called a virtual DOM. I told you I'd mention the virtual DOM. This HTML that we're outputting is not actually the DOM node. It looks like it, and to a first order approximation, it roughly is. But what this is a very lightweight representation of the node. So that button, you can't call .click on it. You'd have to actually get a reference to the actual DOM node if you wanted to call .click. But conceptually, it is a button. And when you render that to the output, it will be a button. And just to stop for a second, virtual DOM is very different from shadow DOM. If you know what a shadow DOM is about encapsulating your components such that things are not visible from outside components. It's a web component term. The virtual DOM is completely unrelated. Shadow DOM is cool. You should definitely look it up. It's interesting. It's fun. It's all about web components. That's not what we're talking about. So if you were thinking shadow DOM, erase that from your memory. So the virtual DOM, like I mentioned, is fast, lightweight nodes. So these things can be created and thrown away. You can re-render the entire application using these virtual DOM nodes, and it's essentially free. On this laptop, I can create 200,000 virtual DOM nodes in a second. So unless your application has 200,000 DOM nodes, it'll render in under a second. And then once we have these virtual DOM nodes, what are we trying to accomplish with this? Like, why are we using a virtual DOM instead of using the real DOM? Real DOM nodes are very heavyweight and very expensive. If you set a value in a real DOM node and then subsequently read values from those DOM nodes, you can force what's called a reflow. That forces the browser to recalculate the layout of the page. And this is a very expensive operation. Generally speaking, if you're writing a large web app and you want it to be performant, you're going to try to avoid reflows as much as you can. It's really difficult with handwritten JavaScript to do that, whereas with React it's sort of automatic because of our last thing, we queue updates. So what we're going to do with this virtual DOM, we take the output of a render, we figure out what has changed, we figure out what all the updates that we need to apply to the DOM are, and then we apply them all at once in rapid succession. We don't perform any reads. It's a pure write cycle. And that means that we only have a single reflow at the end. So this is how we achieve the performance characteristics that we do. This is how we're able to effectively re-render your entire application every single time and have all those changes be fast. OK, so I sort of alluded to what was going on here. Now we're going to make it a little bit more explicit. We have a virtual DOM at t=1, and it has some state. So your application is a tree of DOM nodes. This should be familiar to you. And we have it generated based on some set of data. What we then do is the data changes. The underlying application gets some new information. And it's going to re-render the entire application, or entire web page application from the start. It's going to generate a new virtual DOM tree. We say t=2, time is equal to 2. Now we have a new tree. And what we're going to do is traverse this tree and figure out what the differences are. So we see that we've added a yellow node, and we removed the red node. So those are our two changes. And what we create is effectively a list of mutations. This is a list of operations that need to be applied. Sort of an interesting side note is that the virtual DOM at t=1 and t=2 doesn't have any DOM nodes. You could actually run that in a separate context. You could run that, for example, inside of a web worker and send the mutations over a serialization boundary. I'm not sure if that's a good idea, but conceptually it is possible. This list of mutations at the end is just simply applied to the DOM, and that's what changes your application from its previous state into the new state. Okay, so reconciliation. This is the process of updating the UI of your application to match the state. So this is exactly what we were talking about. Basically, the reconciler is the module within React that crawls through all of the DOM nodes and figures out what needs to change. To calculate a truly minimal diff, it's a n-cubed operation, which n-cubed is a large quadratic. Obviously, that's going to be slow. For 1,000 DOM nodes, it would basically be prohibitively expensive. And applications could easily have 1,000 DOM nodes. So what we did is we implemented a reconciler that runs in O of n time. And that means that you can render thousands or tens of thousands of nodes, and React is still fast. How did we do that? React is obviously not magic. React is written in JavaScript, which means that anything that you could do in React, you could do in JavaScript. There's no magic happening here. Basically, you could always tune your application just like dropping into assembler. You could always write whatever you could write in C. Same with JavaScript. But basically, the way that we do this is we take some shortcuts. We figure out sort of what the characteristics are of a typical application and how we can use heuristics to cut down the n-cubed factor. So one of the heuristics that we use is we traverse in levels from top down. So each component is going to render a set of children, and we only reconcile within that set of children. So that means that DOM nodes can't move from somewhere near the bottom of the tree or the middle of the tree up to the top of the tree. That move won't happen. Basically, what would happen is the DOM node in the middle or bottom of the tree would get deleted, and a new DOM node up at the top would get created. So it would be a new instance. But generally, this works pretty well because things might move around within DOM nodes. You might have a list of items, and that list gets reordered, for example, or a new item gets added to the back, or a new item gets added to the front. But most likely, you aren't going to add those items randomly in your application at random locations. And so you have a list component on top. You have the children underneath that you add or remove to. It's a completely natural way of reasoning about your application. And it also happens to be very performant because now you don't need to walk everywhere to find where nodes might move to. Another optimization hint that we use is we look at the type of the component that you're rendering. So an example is if you have a comment box and you have an image gallery. Those are two separate component types. Comment box does not equal image gallery. And so if you were to stop rendering a comment box and start rendering a image gallery, we'd say, you know what, this is it's not likely that you're going to reuse a lot of these DOM nodes. So we're going to throw away that tree and re-render the image gallery. And this has the side effect that any state within the DOM nodes from the text box won't exist in the image gallery, which is sort of the behavior you want. Because if somebody started typing into a text box and maybe you have a comment box in the image gallery, you don't want that to happen to overlap. And it just so happens that that DOM node was reused, and so the user's comment exists there. That's really not what you want. So reconciliation by type makes a lot of sense. Similarly, if you rendered a comment box last time and it had 10 comments, and you render a new comment box this time t equals 2, and it has 11 comments, most likely what that was is the user added a new comment or got a new comment inside of their comment box. And so reusing those previous 10 nodes makes perfect sense. It's possible that we'd have to go and update one of those nodes, so change a value inside of them, but reusing the DOM nodes makes a lot of sense. So that's another heuristic that we use. So let's look at what reconciliation does. Here I render 5 circles at time t equals 1. At time t equals 2, I render 6 circles. So what's going to happen? We start off with 5 circles. We add a 6th circle to the bottom. Basically what we're doing is we're mapping each of the existing DOM nodes into our new set of DOM nodes. So the virtual DOM specified 5 and 6, and so that's what we get. We reuse as much as possible. And basically at the end, we just add the DOM node because we could add it anywhere. To be clear, it would be perfectly correct for React to have put that red node anywhere. That new circle is not differentiated from any of the other circles. So it could just as easily have gone in the front or the middle or wherever. In order to allow the user to specify order and also to allow for the correct reuse of DOM nodes, there's an optional key parameter that you can specify. So you can specify that the circles, A, B, C, D, E, and then A, B, C, X, X, D, E. And so this is going to sort of do exactly what you would expect. We're going to say that XX appears in between C and D. One of the key characteristics here is that DOM nodes can have state. In particular, a text input box, for example, you could be entering text into that box. And so if each of these circles had a text box inside of it, you really want that text box to be reused correctly. It's not enough to just add another circle. You want it to reuse the same DOM nodes. And for text box, you could read the value, keep that in application state, re-render, and pass that value down such that no matter whether those DOM nodes are reused or not, the text box value is retained. But it turns out that not all DOM nodes can have their state read. And so the only way to maintain that state is to reconcile correctly. An example of this is the file input. You can't read the value of that for security reasons. And there are others. Basically, the only way to preserve those values is to reconcile correctly. And so that's why it's important to specify keys. And I'll talk a little bit more about that in a second. But we could also have specified completely different keys. So A, B, C, D, E, V, W, X, Y, Z. What's going to happen here is you're telling React explicitly, do not reuse any DOM nodes. Recreate the DOM nodes from scratch. You might want to do this, for example, to eliminate any of this persistent state that could have been in the DOM nodes. But it's also why key can't be a random number. One thing that new React users might try is to use as their key math.rand, because it gets rid of all the warnings and errors, and basically their application renders the way they expect every single time, except they would lose any internal state inside of their application. So it's really not what you want. What you want is to tie the key to the meaningful identity of that node. You could also specify keys just as the number that exists inside. So if you're iterating over a list of comments, for example, index 1, index 2, index 3, you just use that as your key. That would add a key to the back. So this is exactly what the default rendering algorithm does. So by default, the reconciler doesn't have any other information. So if you don't specify a key, it will just use the index of your node as the key. And you'll see that that's why we came up with this behavior. This looks exactly the same as the output when we didn't specify a key. And the reason is because we're using index. But in general, this is not the solution you want, because the index in the array doesn't really identify that item. It would be much better if you have comments in a comment box, for example, to use a checksum hash of the comment, or an ID of the comment, or something that really identifies that entity, that thing that you're talking about. If you think about it as identity, then everything really works out much more naturally. You maximize DOM node reuse You preserve DOM state, you preserve application state, you sort of preserve exactly what you want. So it is a performance optimization. One of the reasons that we use keys is that it allows us to find items and reorder items and sort items very quickly. But it's also really about identity. And this is sort of a key point that I want to like make sure we drive home, that keys are about identity in addition to performance. Reconciliation, so basically there's a whole bunch of other topics on reconciliation. That was sort of a high-level overview of how the process works. Subtree rendering because of set state is an optimization basically where you set state deep inside of the tree, which means you don't have to reconcile the entire tree because you know where in the subtree the state has changed, and so you only need to reconcile from that point on. Selective subtree re-rendering is basically, it allows you to specify whether or not you want a subtree to re-render. So if you know that something is static, that like, given this input, it hasn't changed, it's a potential optimization. Batched updates is a optimization. Currently, it can be applied in userland, and one of the things that we're working on right now is applying it in general. But conceptually, the idea is that if your application receives 3 updates in rapid succession, that is, this piece of data changes, and then that piece of data changes, this other piece of data changes, you can batch all of those together and do it in a single flush so that you aren't basically constantly reflowing the DOM. You aren't thrashing the DOM. So lots of other optimizations. A lot of these are discussed online in GitHub issues on the website. So I would encourage you to check them out if sort of you're interested in reconciliation and in React. And we're actually rewriting the reconciler currently to handle sort of concurrency and to allow the reconciler to yield at any time. So it's sort of a really opportune time if you do want to dive in. We'd love to take PRs and to talk online. So basically, today, just a brief overview. React's design, we have simple components that are used for rendering the view layer. Conceptually, we re-render the whole application after every update. So applications flow from top to bottom, and you're always following the same code path, so you avoid this constant state transitions and state mutations, which is avoiding the n² minus n transition complexity. I mentioned the virtual DOM, lightweight descriptors that specify the desired render tree. So basically, React outputs virtual DOM nodes, which are then diffed and reconciled to the real DOM. And the reconciliation is the process of actually doing that. So that's what I had for you guys. Went a little bit early, so if you guys have questions, I'm happy to field those. Yeah?
How does the actual DOM know not to reflow when you're moving a bunch of changes out of the virtual DOM to the actual DOM? What makes it not crash when you're writing the batch?
So the question was, what makes the real DOM not thrash when we're writing everything after we've done our reconciliation? And what happens here is that we never do a read from the DOM. And what forces the reflow is reads. Whether that's the browser actually reading it to render it at the end, or whether that is because like you're imperatively set this value, set that value, read this other value. Basically, reads are the expensive thing. The DOM knows, the browser knows not to finish, or not to actually read from the DOM until you have relinquished control. So until you've said, okay, I've done everything I'm going to do, I'm exiting my JavaScript call now, the browser knows not to do a read. And we explicitly don't do any reads. And so as a result, the browser won't thrash, and you won't have any reflows. Good question. Yes?
So we had a conversation internally in our group recently what virtual DOM we should use. And so we had used Angular, and then Angular 2 came out, and that made everybody pretty upset. And we were looking for a roadmap for React, and we found it pretty difficult to sort of find the direction that Facebook intended to take with React. I realize this is probably an answered question, but I was wondering if you could sort of explain what that direction is or where we can find it. Or
so this is the direction for what in particular?
For where like React is going. So like you just released version 15. Like where's what's the direction, and like how do we stay sort of up to speed on what to expect in the future?
Yeah. So this has been one of the things that we're actually actively working on in the community, is sort of communicating this better. We just at our last team meeting had a discussion about introducing like an RFC process so that people have more visibility into what we're talking about, what we're thinking about, what we're doing. Basically, there are several things that we're working on in parallel. One of the most major ones right now is figuring out how to make the reconciler incremental. So it's this idea that we want to be able to yield control of the reconciler at any time so that we can process a high priority update, for example. It doesn't get blocked by a low priority update. Or so that we can basically do things without ever dropping a frame. Because if you take more than 16 milliseconds, you're going to drop a frame. And ideally, we would avoid that. So incremental reconciliation is a big one. Another roadmap thing that we want to do is again, probably longer term, is get the actual layout information into React. So right now, what React does is it generates some HTML. It throws the HTML out over a wall into the browser, and the browser handles layout. One thing that we would really like to do is be able to have React know exactly, this box is X pixels long. It, comes, in this position on the screen, to know exactly where each of the DOM nodes are. And the reason for this is that if you know the layout information, then you can make a lot of high performance optimizations. For example, if you have a scroll list with 10,000 items, you don't need to render all 10,000 items. You only need to render the 5 items that are on screen. And so if we have layout information inside of React, we can do optimizations with regards to like what we render, where we spend our time. This goes into the incremental reconciler where if we know where to spend our time, then we can focus on things that are going to be on screen and render things that are just off screen when we have extra time. Another priority is sort of inline styles. That's one that the community has had a lot more input on and been driving forward a lot more. The idea there is that you can specify your styles in JavaScript instead of specifying them in CSS. And that leads to better encapsulation, better modularization of components. It allows you to share components more easily and not worry about conflicting CSS styles. So those are some of the big things. Every release, we have an issue that we create. It has the word umbrella in it. So for version 15, it was like version 15 umbrella or 0.15 umbrella. And if you search for the umbrella issues, then as we figure out what we're going to actually put into a release and what we want to work on, we'll create that issue. We'll have a bunch of checkboxes and check that off. So that's probably the easiest way to get a roadmap.
Thank you.
Yeah.
You'll have to excuse my question. I'm a little bit ignorant of the kind of implementation details of the DOM inside of the browser. But so in the initial example that you showed with the bell, the reason that original JavaScript was hard to read was because you had to check the state before you made the update, because presumably if a piece of state, you couldn't just say, given this condition, there's fire. You had to say, given this condition, if there's not already fire, add fire. You had to know what the current state was. I guess I'm wondering, just at like a 10,000 foot view, why is that expensive, and why can't the browser itself optimize those updates away so that I could just write code, and if the current state of the UI is what it is, that's not an expensive update? Does that make sense?
It does make sense. So the question was, basically the reason that this code is complicated is because we have to read the value every single time. And also, sort of, why is that expensive? So there's two parts of that question, and I want to sort of talk about how they're different. So one part is code complexity, and the other part is browser performance. And there's sort of orthogonal issues. But with regards to code complexity, building this into the browser wouldn't solve the code complexity problem. Solving the performance problem I'll talk about in a second. But basically, the state transitions that occur, if you model the transitions, if your code is responsible for bringing you from one state to another state, you're going to have that complexity because you have to do those reads because you have to know the state, the previous state, in order to get to the new state. If you did not need to do that, if you didn't need to know what the previous state was in order to render the new state, that is basically React. So browsers could build React into the browser, and that would solve this problem. But then the question becomes, why would you build React into the browser when you can have React in user land? Basically, the browser provides the fundamentals that you need, and library authors are free to build whatever abstractions on top of that they want. React is one such abstraction, and we get a million JavaScript frameworks every year. Who knows? Maybe you guys will have the next idea, hopefully building on what we've done here, and build the next one. So that's sort of why browsers haven't built in the declarative layer, is because it can be done in user land. And that would solve the code complexity problem. That's one thing that React solves. The other issue is a performance question. So why are these things expensive? Why can't the browser just make it fast? And part of the reason for that is that the browser needs to know, the browser allows you to ask a lot of questions. Some of those questions are about things that you didn't actually need the browser to tell you. For example, did you previously have Fire and now you don't have Fire? But other things that you could ask are like, what is the position of this element? What are the effective styles on this element? And these things require a reflow. And so if you ask the question, then you're potentially triggering one of these reflows. You're forcing the browser to do a lot of work. And the way that React is designed, it allows you, basically, React knows what it had previously, and so it knows all the things that could need to change. Thus, it doesn't need to ask any questions. And so it doesn't need to involve the browser. The browser doesn't need to do a reflow in order to figure out the answer. So that's the performance.
Cool, thanks.
Yep. JSX versus pure JavaScript. Every time we see people write React to JSX, and I wonder if anybody. So the question is, every time I see somebody write React, it's in JSX, and I wonder if anybody does it in just pure JavaScript, if there's any reason for it, if you've seen it.
Yeah, so there are a few people who use React without JSX. We support it because it's something that primarily people have an initial aversion to JSX. They're like, I don't want to do that yet. Like, they're not that invested. And so generally, they'll write pure JavaScript. If they don't have a transformation pipeline in their development cycle, that is, if they just write files, hit save, refresh their browser, and expect it to show up, that's sort of another reason to not use JSX. JSX does require that you transpile from the source language into the target language. There are a few companies who use it, or who use just pure JavaScript API. But in general, people really like JSX. Once they start using it, they feel that it really does simplify their code, make everything much more readable. And so it's been sort of a crazy success. The other aspect, or the other place that JSX is sort of pseudo-used is other languages will transpile to JavaScript. So for example, there's TypeScript, there's Clojure, there's a bunch of other languages that generally, their syntax, as far as I know, all looks like JSX does, but there's no reason why it would have to. So by providing a standard DOM interface, what we're doing is allowing other languages to transpile to React code. So you don't even have to write it in JavaScript if you don't want to. Yeah.
When reconciling When reconciling, does React ever read from the actual DOM to detect changes that have come from outside React, say from a browser extension or a bookmarklet or something like that?
Good question. No, React will not read from the DOM. And that's largely for performance reasons. But another reason that we don't even try is that a Chrome extension, for example, could do absolutely anything. It's completely unpredictable. And there's no way to programmatically reason about this. The absolute best we could do is just blow away those changes and say, like, you know what, that's not a change that we're going to have applied, and the Chrome extension basically becomes useless at that point. But there's sort of not much of a reason for that. If the Chrome extension plays nicely, then basically both entities can mutate the DOM simultaneously. If it's just like applying a style or something, that's probably just fine. In general, that's not supported though, and if people change the DOM under your feet, things can break. That's a fact of any web application. To be clear, that's no different than if you were to write your own JavaScript. So if you wrote your own application and you like add a Fire node and there was something else there already, and you like blow it away, or it causes somebody deletes a node that you expected to be there, and you NPE, like there's sort of not much you can do about that. So no, we won't read the DOM, and that's largely for performance. Yeah.
How much, if any, is code shared between React.js and React Native? Are they similar code bases, or is it just like similar APIs?
Great question. So we have a product called React Native. React.js was sort of our first iteration, our first thing that we built. That's why it gets the name, which is synonymous with the core. That targets the DOM. We also have React Native, which targets mobile phones. So this is a question about like using React on Android, using React on iOS to render to native iOS and Android components and widgets instead of DOM widgets. And there's other native renderers. You can render to SVG, you can render to Canvas, you can render to desktop now. So basically, there's a whole family of renderers all related to React.js. And the question is, like, how much code sharing is there? How much of that is just similar API re-implemented? Basically, React Core and React.js are very tightly coupled right now. We're working on separating them, but right now they're a single entity. React Core is sort of what I work on. So that's the thing that does all the heavy lifting of React. React Native is a layer built on top of that. So when you install React Native, you're basically getting all of React.js, modulo a few things that we're stripping out, and we're slowly stripping out more and more of it. But basically, React Native is a component layer. It's a bunch of components built on top of React.js. The important thing is that the API is the same. It doesn't actually matter how much is reused. Right now, a lot of it is reused. But the important thing is that components from React Native have the same interface as components from React Web, which means that to a large extent, you can take a React Native component, plop it in a browser, and run it in the website, and vice versa. You just have to basically polyfill the underpinnings. Good question. Yeah?
So first, just to check my understanding, after reconciliation, the virtual DOM, the new one, that lives until the next reconciliation. Is that right? And then it becomes garbage and kind of goes like a pipeline like that?
That's exactly correct.
So have you studied the GC behavior, and does this cause many GCs? Because you might hope the generational GC would clean it all up, but it seems things would be living just long enough to survive a generational GC and move into the tenure heap.
Yep, that's exactly true. That's one of the things that we are sort of actively looking into, is how can we work with garbage collectors better. It turns out that the garbage collection characteristics on mobile phones are different from the garbage collection characteristics on web. And so the answer is yes, it's complicated, and it is unfortunate that we retain those references for so long. Our new syntax, stateless functional components, is largely in the hopes that we'll be able to sort of mitigate some of those things. So we could do things with incremental reconciliation and stateless components like re-render using the old data, re-render using the new data in a single render cycle, do the comparison on the fly. So basically you perform 2 renders, you compare them, you figure out what the diff is going to be, and you send that to the DOM. And then you throw both of them away until the next re-render happens. We don't do that right now. It's one of the things that we are exploring in the hopes of better utilizing the young generation. Jury's still out on whether or not that's useful or practical. Cool. Oh, question?
What are the disadvantages of using virtual DOM independent of React?
Advantages and disadvantages of using virtual DOM independent of React. If it works for you, excellent. More power to you. Basically, React provides what we think is sort of the minimal set of useful, like a minimal set of useful APIs that will allow you to sort of optimally render your page. Using virtual DOM without React means that you need to decide when to re-render your components, if you even use components. You need to decide like how you're going to basically structure your application. Certainly if you want to use virtual DOM as a performance optimization to avoid DOM mutations and DOM writes, there's no reason why you couldn't do that, and if it works for you, that's great. Yep.
First of all, thanks for the talk. It was great. Back to managing complexity. So how would you re-envision this Bell component with maybe 3 states so that this mess doesn't happen?
How would you revision the Bell component with 3 states that mess doesn't happen? So the way I would do it, well, I don't know where the code went, but basically I would re-render from the beginning. I'm not sure like what you can do to avoid, like if you have to transition between states, then you have to do those transitions. You could, for example, blow away the node every time and just re-render it from scratch. So you could say, every time we need to make a change to this bell, we're going to delete the bell widget and re-render it. That's what React does sort of conceptually, but React just simply applies performance optimizations and state retention characteristics that make it better. So basically, the way we would re-envision it is the way that we built React. Yeah, basically, there's a lot of disadvantages to blowing away the DOM node. For example, if you blow away an entire comment list, then you might cause the scroll bar to move, because now you have a new elements, new position. You deleted one, added another one. So there's sort of a lot of things that go wrong when you blow away nodes. That's why React jumps through hoops to retain and reuse as much as possible. But yeah, I think that's the problem with the imperative model, is it's basically unavoidable. Yep.
So when you were talking about the React team reworking reconciliation before, and also that makes me think of you were talking about yielding at any time, which makes me think of ES 2015 generators, which you could use with Babel, and then you were talking about accessing layout, which makes me think of CSS Houdini or something. Are there any technologies that the React team is excited about, or maybe even have a hand in, that are hopefully going to let you guys advance further?
Yes. So we actually have a list of them. Maybe I can pull it up real quick. Basically, I guess we'll get that later. Now I lost my slides. Looks like I lost my slides. Yes, so basically there are technologies. One that we were really excited about and did get was the, it's remaining time. I can't remember the exact name of the function now, but it's basically the amount of time that remains in the current frame so that you can continue to render inside of that. You can continue rendering for that amount of time and still hit your frame target. Ones that we're excited about that are upcoming, so compositor threads, compositor workers is a big one. Let me see if I can pull up that list. I cannot. Maybe. I'll try to find the list for you. I don't remember them offhand. So Sebastian is our TC39 representative, and he is the one who's most excited about new technologies and is always thinking about what's coming next. Cool. I think we'll call it a day. Thank you guys very much for being here. And